Welcome to session number 14. In today's session, we're going to have a bit of a review of all the stuff we did last time, which was quite complex, a lot of new concepts, and then we're going to continue our discussion of the metal semiconductor or Schottky junction, also known as Schottky barrier. But first, let's listen to a wonderful performance of the finale to Haydn Cello Concerto in C major, and we'll see you back in about 6 minutes. Okay, these are some of the topics we'll be covering today. We're going to review a little bit from session 13 because there was a lot of material there. And this will be the N-type silicon Schottky barrier in equilibrium. Then we're going to look at just a little bit of something called surface potential. Then we'll go into the main body of our work for today, which is P-type silicon in contact with a metal work function in B sub M, where we'll look at the conditions under which we get a rectifying junction under the... Okay, so these are some of the topics I'll be covering today. We're going to have a little bit of a review because last time there was a lot of new material and it may have been a little bit intimidating. So we're going to review the N-type silicon Schottky barrier, which is rectifying, and we'll explain what that means again. Then we'll look a little bit at the surface potential, and then we'll go to the main body of what we'll be covering today, which is P-type silicon in contact with a metal, which also will be rectifying. And by rectifying, I mean that there is an area close to the metallurgical junction, metallurgical junction being the point where the metal and the silicon meet physically. There is an area in the silicon, not in the metal, in the silicon which is depleted of mobile charge. And if we have this so-called depletion region, then we will have a rectifying junction. Then we'll talk about how wide that region is. How wide is the depletion region? We're going to call that the width W. And if there is a depletion region, there is band bending. Why? Because if there is a depletion region, there are fixed charges. There's fixed ions. If it's in N-type silicon, those ions are positive. If it's in P-type silicon, those ions are negative. And if there are fixed charges, there is an electric field. And if there is an electric field, there is band bending. So depletion width, electric field, band bending all go together. Then we're going to talk about the opposite when we have non-rectifying junctions, where we don't have a depletion region. No depletion region, no electric field, no band bending, non-rectifying, or what we call ohmic. Now, we don't use this in practice to make ohmic contacts, but at least in theory it's interesting to understand what the issues are. Then finally, if we have time, which I hope we will, probably won't, but who knows, we'll talk about the depletion capacitance in a rectifying Schottky barrier junction. If there is a rectifying Schottky barrier junction, I'll just repeat, there is a depletion region, there is an electric field, and there is band bending. And because there is a region which is depleted of mobile charge, it looks like a capacitor. So we're going to talk about the depletion capacitance in a rectifying Schottky barrier junction. Okay, so let's get started. This is a bit of a review. For N-type silicon, such that, and this is important, rectifying junctions in N-type silicon require that the work function in the metal is greater than the work function in the silicon. Therefore, the Fermi level in the silicon is higher than in the metal. Therefore, electrons flow or transferred from the silicon into the metal. Now, in the metal, there is no conduction band edge or valence band edge or intrinsic level. There's only a Fermi level and a free electron level. And the difference between the Fermi level and the free electron level is called the metal work function. Electrons in the silicon at the metallurgical junction, we said, have higher energy because they have a lower work function, so that electron flow from the silicon to the metal, and that's what we're going to have. And because we have that flow or transfer, we uncover positive ions that were originally doped donor atoms, but since they donated their electrons into the conduction band, they become positive donor ions. A field implies band bending, that's what we said before, and this is important, and we'll prove it a little bit later on, but just for now, just keep it in mind that the N silicon bands always bend up, and because the conduction band edge, the valence band edge, intrinsic, and E0 all follow together, they all bend up. So everything bends up in N-type silicon in a rectifying junction, and we'll find, and you can probably kind of guess because everything stands on its head, in P-type. For P-type, they always will bend down. And again, I don't have a good mnemonic for that. P-type always bends down, N-type always bends up, and that's really important to draw the energy band diagram. So keeping that in mind, it becomes relatively straightforward to draw the energy band diagram. And we found last time, and we'll just show it again, both for P-type and N-type, the band bending is equal to the difference in the metal and the silicon work functions. For N-type, it's phi sub m minus phi sub s. For P-type, it's going to be opposite because phi sub m will be less than phi sub s, so it will be phi sub s minus phi sub m. But that's expected because everything we say in P-type is opposite from what we say in N-type. Okay. The magnitude of the depletion region width, the W, which we mentioned in our first slide, is, here it is right here. The magnitude of W generally depends on the doping level. Now, before we get started, just some typical work functions of some common metals. The most common in silicon is aluminum. We have these others. They are not quite as common. You'll see they're all centered around 4.3 to 4.6 or so, except for manganese, which is on the low side, and gold and nickel, which are on these are kind of the outliners. They're on the high side. And these are very useful when we get to, oh boy, this is a long way off, chapter 24, I believe. We talk about MESFETs. Gallium arsenide MESFETs use gold because it has a very high work function. And something called a static induction transistor uses nickel also because it has a very high work function. Okay, if we look at some of the affinities for common semiconductors, they're all centered around 4 to 4.1, except for one outlier in indium phosphide. There's always one special crazy case, which is about 4.4, but all the others are about 4.0 to 4.1. Silicon carbide has a range of affinities depending on the particular structure of the silicon carbide. And I've included one non-semiconductor, namely silicon dioxide glass, which has a very low affinity. It has a very high band gap. In fact, it's not even a semiconductor. If we think of it as a semiconductor, its band gap would be about 9, but it has a very low affinity. So this section is essentially a little bit of a curiosity. The point here is that because we have a depletion region W, which does not contain mobile charge, we have a region in which the doping in an N-type silicon is much less. In fact, it's pretty close to intrinsic compared to the interior. And you can see that here. the doping in this region, this is the depletion region, and it extends a width W from this point, which is the metallurgical junction, until the interior, and everything to the right here will be known as, actually three terms, I think, quasi-neutral. I don't know why they say quasi. It's neutral because the positive ions are balanced by a sea of electrons. It's also called bulk because that's the bulk stuff. This is a very small region, about 0.1 to 0.3 microns. This can be a number of microns, and it's also referred to as an interior. Okay. So the doping level is less, and the doping level, of course, it determines the difference between the Fermi level and intrinsic. And as ND increases, Fermi level moves further away from E sub I in the bulk. The difference between the work functions is precisely equal to the amount of band bending. So what we say here is the electron affinity for silicon is 4.05. Somewhere up here, where it is, 4.05. So we just go through. This is just some algebra, not very exciting. And phi sub s, this difference here, this value here, which is the work function in the silicon, is equal to 4.05. The affinity plus what? E sub f minus E sub I plus, the half Eg, which is this distance right here, minus EC minus EF. I'm sorry, EF minus EI. Let's go through that again. I'm sorry. The silicon work function is equal to the affinity plus EC minus EF. EC minus EF, this difference right here. We see if we add the affinity Xi 4.05 plus this little difference, we get phi sub s. So I should have said that first time, but that's fairly clear. And then we take E sub C minus E sub F. E sub C minus E sub F is equal to this distance minus EF minus EI. So if we take 1/2 the band gap, which is EC minus EI, and we subtract EF minus EI, we get EC minus EF. So take 1/2 the band gap, subtract this distance here, and we're left with EC minus EF, which is the function, the quantity over here. So the work function of silicon is, we just add these up, 4.6 minus EF minus EI. And the point here, and this is a little bit of a curiosity, 4.6 is kind of a privileged position. If the work function is on the order of 4.6, then we know that phi sub bi, the band bending, is equal to difference in the work function. So this would go out, this would be 0, and then phi bi would be equal to EF minus EI. Or if we flip it, it would be EI minus EF. It really wouldn't matter, but the point is that we'd be approximately intrinsic. And the fact is that at the surface, in fact, almost throughout this entire region, we're going to assume that it is pretty much intrinsic. So there are essentially no mobile charge in this region. 10 to the 10th is considered essentially, that's intrinsic, and that's considered none. So it acts like a dielectric. And there's just one more issue here, which we'll just mention in passing. In the next chapter, chapter 9, we're going to put an external voltage. And we're going to, by an external voltage, we're going to be able to either increase the band bending or decrease the band bending. So if we have intrinsic in this region and we increase the band bending, one would at least imagine that we could possibly flip the sense and go from N-type to P-type. And in theory, that should be possible. In practice, and we'll show why it's not possible, we really can't do that at all. And however, and this is the takeaway, if we put a real insulator between the metal and the metallurgical junction, we will be able to continue to increase the band bending such that we're actually able to flip the sense from N-type to P-type, and that is the basis of the metal oxide semiconductor field effect transistor. Okay, so now I want to take a look, or at least start, on the P-type silicon in contact with metal work function of phi sub m. Let's take a look at that. For a rectifying junction, we're going to see that the phi sub m is less than the phi sub s. Remember, in the N-type, the phi sub s was smaller than phi sub m. In the P-type, because P-type is flipped from N-type, everything we say about P-type is the opposite from N-type. We have exactly the opposite. So this would be the energy band diagram for the rectifying metal P-type silicon immediately after contact. Are they in equilibrium? No way. They're not in equilibrium because the Fermi levels do not match. So in order to make the Fermi levels match, holes are going to transfer. This is a lot of holes because this is P-type. Holes are going to transfer from the silicon into the metal. The metal Fermi function will, the metal Fermi function will go down, or we can think of the silicon Fermi function, Fermi level, as going up until eventually they meet, and that is the condition right here, where the Fermi levels of the silicon and the Fermi levels of the metal meet. So we have one Fermi level which extends from the metal into the bulk of the silicon, and it is straight and it is horizontal. Okay, so what we have here is the P-type silicon in contact with a metal, and I'm going to claim that the same general arguments, everything turned on its head, but it's still general. The arguments that apply to P-type silicon are really the same as the arguments that apply to the N-type silicon. Because it's P-type, there's abundance of holes near the junction, and because the work function of silicon is greater than the work function in the metal, holes are driven from the silicon into the metal. This is exactly the opposite of what we had for N-type. Okay, so here the structure proceeds towards equilibrium. Holes are flowing out of the junction, and there is a gate which allows holes to flow from the silicon into the metal, but because the holes flow out, there is a depletion region. There's an electric field which extends from left to right. If the electric field extends from left to right, it would tend to want to push holes also from left to right. By definition, the direction of the electric field is the direction that electrically a hole would want to move. But holes are moving right to left. So electrically, they're going to move. We're going to have a situation where the holes are going to want to move from left to right, but in energy, they're moving from right to left. So eventually, they balance one another out. It works out when that balance becomes exactly equal. The electrical forces are equal to the energy forces. Electrical forces left to right, energy forces right to left. When they exactly balance out, that's when the Fermi levels precisely equilibrate. And here we show the progress. The holes are flowing from the silicon into the metal. There's less holes at the depletion region. However, in the bulk, there's still the same density of holes that we had before we put the two levels together. So if we had 10 to the 17th in the bulk, we still have 10 to the 17th in the bulk, even after we form a junction. Okay, so the idea is here that just as we found values for the barrier heights, with the barrier heights, the phi bi and the phi bn for n-type, we're going to do the same thing for p-type. We're going to find a phi bi, and we're going to find a phi bp, not n. Okay, so refer to figure 827. There it is. And I'd like to find out what the phi bi is. This is the phi bi, this is the phi bi, and this is the phi bi. So just from the figure, we just take the metal work function, we just kind of scoot it over here, and we know that the silicon work function is greater than the metal work function. And if we take their difference, I sub s minus I sub m, we get, well, this distance right here. Just sort of move that over. Phi sub s minus phi sub m is equal to phi sub bi. Well, that should look familiar. The amount of band bending is equal to the difference in the work function. The only difference here is that since the silicon work function is greater than the metal work function, it's just flipped. The magnitude is the same, but the sign is flipped. And again, that is a consequence of whatever we have for P. We have exactly the same thing, except reversed for N. So if we have something for N, we reverse it, and we get the same thing for P, more or less. And that's not always the case, but more or less. Okay, now we want to find phi bp. So we want to first put that in terms of phi bi. Oh, the other thing I should mention before we go on here, I sub m is not a function of doping. It's only it's a characteristic of the metal only. Each metal has its own specific work function, but the phi sub s is a function of doping because the Fermi level rises and falls with doping. If the doping was greater, it would fall, and phi sub s would even be bigger. Okay. Phi sub bp, however, this bad boy right over here, should not be a function of doping. It'll be a constant. And let's see if that is indeed the case. So phi bp is equal to phi bi plus this little difference here, the difference between the Fermi level and the valence band. So if we add this distance here to phi bi, we get phi bp. But phi bi, we know, is phi sub s minus phi sub m. That's what we just found up over here. So we just substitute that in. And what is this bad boy over here? Okay, this is a little bit more complicated, but not so much. I'm going to claim that this distance here is equal to xi, the affinity in the silicon, plus Eg, which is this total distance from E0 to the valence band edge. Okay, that's this minus phi sub s. And we can see that right here. We take this total distance, we take away phi sub s, what do we have left? Right there. And that's what we're looking for. The difference between the Fermi level and the valence band edge. So we put all that in, we see phi sub s over here, phi sub s over here, we cancel it out, and we have that phi sub bp is equal to xi, which is constant, Eg, which is constant, minus phi sub m, which is constant. Nothing depends on the doping, and that's repeated here in equation A26, and that's a big deal. Okay, so we have one barrier, which is a function of doping, and the other barrier, which is not a function of doping. Okay, so we just repeated the energy band diagram for p-type silicon in contact with a metal function, where the metal function is less than the silicon function. It's rectifying. We know it's rectifying because we have band bending. If we have band bending, we have a field, we have a depletion region, and that should be clear, I hope, after repeating it too many times. Okay, so just in summary, we have the phi bi is equal to difference in work functions. In this case, I have flipped it. Probably not the best idea to do this. So this guy would be negative, and if I want to make it positive, I just reverse it. Okay, and the relationship between phi bn or phi bi and phi bp, which we started with back up here. Phi bp and phi bi. Okay, so let's take a slight detour and ask two, hopefully not totally idiotic questions. Why is the depletion region parabolic? Well, I was going to say if you were following attention, but let's just go through it and make sure that we understand this. The depletion region is parabolic. You see, it's always parabolic. It's parabolic for P, and it is parabolic for N. And it bends up parabolic. P, it bends down parabolic. That will be true for the Schottky. It'll be true for the BJT. It'll be true for the PN. It'll be true for the MOS and for the MOS FET. Everything's true. P always bends down, N always bends down. Okay. Why parabolic? It's parabolic because here, this depletion region is filled with, in the P case, it's filled with negative boron or arsenic ions, which have donated their electrons, or accepted electrons from the valence band and become positive. But it is a constant positive value. And here, for the N-type, the phosphorus atoms have donated their electrons, and they become, what, positive or negative? If you donate an electron, you were neutral, you become positive. So here it's positive ions, and it's constant value of positive ions. And here it is a constant value of negative ions. Now the trick is to remember that if we start with the parabolic energy and we differentiate a parabolic, we get a linear. What's the derivative of the charge density from Poisson's equation? And we'll look at it in a little bit more detail in just a second. It's the electric field. So the electric field is linear, the charge density is constant, and if we differentiate the electric field with respect to position, we get charge density. And charge density is constant because the electric field is linear. Differentiating a linear with respect to x gives us a constant. And that will always be the case. A constant charge density gives a linear electric field, which gives a parabolic energy or voltage. A linearly varying, and we mentioned this before, but it's worth repeating, because there are some examples that one does in this, a linearly varying charge density gives a parabolic electric field and a cubic energy. Okay, good. So, why do we refer to the device as a Schottky barrier? What's the barrier part of this? We're going to be applying electric voltages in our next section, and we're going to just give an introduction to it in this session. But let's say we apply an electric voltage such that the left side is positive and the right side is negative. So the right side being negative, it pushes electrons from right to left, and here we see an electron being pushed from right to left. The electric field is left to right. It's in the positive direction. Positive over here, negative over here. So the electron is going along its way. It's really happy. It's going down an energy barrier just like it always loves to do until it finally, well, you can think you're on a sled and it's snowing. And the snow when you're going down a hill, and all of a sudden, whoop, kerblunk, you hit this huge barrier. There's just no way that this electron is going to surmount that barrier. And that's why it's called a Schottky barrier. The same thing will happen in PN junctions and in BJTs, bipolar junction transistors. So the barrier comes from the fact that electrons like to go down smoothly, but they come to this point where they see this huge voltage. It's like running into a 10-foot wall, concrete wall, and there's just no way they're going to surmount this. Now, the other thing that happens when we apply a voltage, we can either reduce the magnitude of VPI or increase the magnitude of VPI. Okay, so the last few minutes, I just want to introduce these concepts of the depletion width, the electric field in metal semiconductor structures in equilibrium. And we'll talk just a little bit about non-rectifying, just make some general remarks, and we'll start an introduction to something called the depletion capacitance. So, all that in a couple of minutes. I don't know how I'm going to do it. Let's see. Anyway, we start to find the depletion width W. That's a big deal. We want to know what the extent, there is W from the interface where the depletion region meets the bulk, that's right here, to the metallurgical junction, which is right here. This distance here is W. For P, we have the P-type silicon, and of course we have the same thing for an N-type silicon, except the bands bend up. I should continue to emphasize that. Okay, so let me give this detour. This is Poisson's equation. This will tell us what the magnitude of the depletion region width is. This is the thing which will tell us what is W. So that's a big deal. And again, we see the second derivative of the energy with respect to position is equal to the charge density, which is constant, divided by the permittivity, which is equal to the first derivative of the electric field with respect to position. So if this guy is constant, we integrate a constant, we get a linear. We integrate a linear, we get a parabolic. So that's just essentially the repeat of what we had said before. And the epsilon is always in the denominator in Poisson's equation. So, in the depletion region for N-type, could be P-type, we'd have a P here. It's constant, and the voltage is simply the electric field per unit charge. And putting all that stuff, we will do it in the next chapter. We're not going to do it right today. We'll just take a look at some of the parameters here and see if we can reason this crazy thing out. It has a square root, and the reason is because it relates energy to position. Energy, position. And if we do the two integrations, we get a square root. So that's why they have the square root sign in there. Notice it has phi bi on the numerator, and that makes sense also. The more band bending we have, I can look at here, the more the bands are bent. See, if the bands would start to bend over a really big band bending, then we would have a larger W. But what is not quite so clear is the fact that we have the charge density on the denominator. And the reason for that is there is a certain amount of charge transferred from the silicon to the metal. If that charge is transferred in a very wide range, or as W is very big, then the doping would be relatively small. As we increase the doping, the charge density goes up, and the amount of charge that's transferred doesn't require, in fact, definitely does not require a large W in order to transfer. So if we have a huge doping, say 10 to the 18th or 10 to the 19th, all the charge is concentrated very, very close to the junction, and it takes just a little bit of W to transfer all that charge from the silicon into the metal. So that's why N sub D is in the denominator. I have written here some explanations of why epsilon is in the numerator, and you can read that for yourself. Actually, it works out. It's the same reason that epsilon is in the denominator in Poisson's equation. We went through that quite a bit. It's essentially a statement of the Schottky's principle. And where is that guy? Right here. So if you can read through the explanation here, I read through it, and I wasn't totally confused, so maybe there's something to it. I don't know. Okay. As the permittivity increases, the band bending and the magnitude of the electric field decrease. And that's really the consequence of what this is all about. So higher permittivity, less band bending, electric field decreases, and therefore the W goes up. It's just like making the charge density lighter. It's the same thing. And here are some permittivities. For air, relative permittivity is 1 because there's nothing to polarize. In SiO2, it's 4. Very hard to polarize SiO2. I think it's even harder to polarize diamond. I'm not sure, but I have to look that up. But most of our semiconductors are in the range of 12 to 15. Silicon and gallium arsenide are both 12. Germanium is 16. So germanium is a little bit easier to polarize than silicon. And then we have some very high permittivities. And then metal, we can look upon metal as having a permittivity of essentially infinite, because it's infinitely easy to polarize metal. There's nothing, just a tiny little electric field, and boom, you got a short circuit. So that's a way to understand perhaps the metal permittivity. You just let it go to infinity. Okay, so this is basically, all this stuff is essentially a restatement of what we were saying before. And there is one little cute little thing here. Transitions are not abrupt. And we're going to find that in a Schottky, actually, they are pretty abrupt. They go from maximum electric field to zero electric field. However, when we talk about p-n junctions and other devices, we'll see that the transitions are not nearly that abrupt, and we have a transition which takes place over a very small length called the divide length. So we'll talk about that in detail a little bit later on. Now again, we said that the electric field this is N-type, the electric field is always negative because in the depletion region we have positive ions, positive phosphorus ions, and at the surface of the metallurgical junction we have a surface charge density of negative electrons, so the field goes from right to left in the negative direction, and that's why it is always negative. It is maximum at the interface, and it is zero at the maximum at the metallurgical junction, and it is zero at the interface between the depletion region and the bulk. Okay, so actually we'll probably stop here, and then next time, I'll just mention non-rectifying, because I'm not going to go through all of this material here. This is actually, I think, somewhat extraneous, because the big deal in non-rectifying is in both an NP silicon cases, non-rectifying refers to the case wherein charge, and here we're talking about mobile charge, is transferred not from the silicon to the metal, which makes a depletion region, but rather from the metal to the silicon. So it makes the silicon surface even more conductive than it was before. And therefore there is no depletion region, and there is no electric field in the silicon at the metallurgical junction. And that is really the rationale behind non-rectifying junctions. So we'll start, this is for N-type. Now here, notice we said always N-type, always bends up. Well, that's for rectifying. And rectifying is the most important part. If it's non-rectifying, it actually bends down, but we don't really consider that as an important case, and it really is not. And of course, you can imagine if it bends down in a non-rectifying for N-type, guess what it does for a P-type? I know you knew that. It bends up. Okay. So next time we'll start with the depletion capacitance in a rectifying. That's the most important case. Schottky barrier junction. And we will end with a video clip. It's a performance of the Chopin Nocturne, Opus 9, number 2. This is one of the pieces that every beginning piano student learns, probably in the first or second year. There are two pieces that one learns: For Elise and the Chopin Opus 9, number 2. This is a performance, beautiful performance, arranged for piano and cello. So enjoy, and we'll see you back next time.